So welcome to the lecture. In the previous lecture, we have identified the Minkowski metric tensor as a 0, 2 rank tensor. In terms of basis and component, you can write it in the following way. Eta mu nu denotes the component. It has two lower indices, dx mu, tensor product dx nu gives the basis 0, 2. And we have seen that it is a symmetric tensor, and using this metric tensor, we can map a vector to a one form. So eta takes a vector v and gives us a one. And we denote the component of the one form with the same letter as that of the component of v, but a v index down. This gives rise to something called lowering of index. So, for example, a component of a vector contracted with the indices of Minkowski metric tensor, this gives rise to a component of a one form. And we can do that for a generic tensor with some index, let's say mu, and there is some index. You will get in general lower index at the same position. Now we also know that the theta is a self-inverse. That means theta equal to eta inverse. So then we ask the following question, that if we denote the component of theta by two lower index, can we do that same thing for its inverse? That is, the component of eta inverse denoted by this is this, correct? So answer is no. So let's figure it out. What kind of tensor is eta inverse? So let's start with the definition of inverse. Eta times inverse is identity, and if you write it in the component form, what we will get? Note that component of the identity matrix is nothing but the delta mu nu Kronecker delta, because this is 1 only when mu equal to nu, otherwise it's 0. So it's only have the diagonal elements as 1. Else. Now, what about the left hand side? So left hand side, we must have the same two free indices at the same two position. This is a tensor equation, so which only makes sense that the position of the same free indices remains same in both sides of the equation, otherwise it doesn't mean anything. So if it is, if right hand side has one free indices at up and one free indices down, so it will has to be for the left hand side as well. So now we know that eta is a 0, 2 rank tensor. So it should, the component of it should be denoted by two lower indices. So this lower index go to eta mu, and there should be another one. Now eta times eta inverse is written as a matrix multiplication, so one of the index should be contracted. So this row index should be contracted. Hence, we should have a row up index. Two index can be only contracted when one of them is up and down. That is what we have discussed, and hence the remaining free index mu will go up with the eta inverse. Now from this we can see that the component of the inverse of the Minkowski tensor has two upper index. So this is a component of a 2,0 rank tensor. Comma 0 rank tensor. So eta inverse nothing but mu del rho. This is how you represent a 2,0 rank tensor. Now, just like what we have done with eta, we can also defining a map which relates one form to a vector using this inverse Minkowski tensor. So eta inverse, again eta inverse is symmetric, so it will let's insert a one form omega in one of the slots, and we can show that this gives a vector. This is one form. And we will again denote the component of this vector as same as that of this one form, but with the index up. Hence, we can define something called a raising of index using eta inverse. Okay. So let's take an one form whose component is omega, and it is contracted with the component of the eta inverse, which will simply write as eta but with two index mu, and this will give a component of a vector. And for a generic tensor, eta, let's say it will have some index. All the index is mu here. It will give something at some position. Right? Okay. So now let's look at the inverse Lorentz transformation. Okay. So remember the definition of the Lorentz transformation, which counts the fact that it preserves the Minkowski matrix lambda transpose times eta in the matrix form. So now from this you can rewrite it and get the following: inverse lambda transpose eta. Now let's write this equation in a component. Okay. So let's denote the component of lambda inverse as mu, and this side will have eta inverse, which will have this mu and let's say some index alpha. So remember that again, both sides should have the same type of free indices. So here the mu upstairs, so there will be a free index up, which will go with the component of eta inverse. So there will be mu alpha, and these should be contracted with the indices of these lambda. So it will contract with the index of this downstairs beta, and then again this beta will be contracted with the eta, and have a index nu, right? So now all the indices are correct, and we can now use the raising and lowering of index to see that we can raise this alpha, which will become nu, and lower this beta, which will become nu. This will give mu beta. So we can represent the components of lambda inverse using this notation. So for example, we know that components of one form transforms under inverse Lorentz transformation, and now using this notation, it will simply take the following form. Okay. So this simplifies the notation a bit because we don't have to use this inverse notation again and again. We can simply write using this notation, but be careful about the index position. So for a generic tensor, write the following: T prime, let's say mu1 up to so all the upper indices will transform under Lorentz transformation. Let's say for P, the lower ones will be under the inverse Lorentz transformations, which we now write it as mu1 beta 1 mu q beta, and then we have alpha 1 to alpha P beta 1 to beta. This cleans up the notation. We don't have to use this cumbersome notation of lambda inverse and write the composite. So one more thing, remember that we discussed something called the infinitesimal Lorentz transformation. Let's revisit that. First of all, remember that we can only define infinitesimal Lorentz transformation for the proper Lorentz transformation, and also as we discussed earlier, that we will only focus about the proper orthochronous Lorentz transformation. So let's stick to that, which means we will have determinant of the lambda is +1 and lambda 0, 0 is greater than equal to plus. Okay. And remember that we can write the infinitesimal transformation as lambda, some identity, plus some small element omega. Okay. Now, in terms of component, we have component. What is this? This will be 1 mu, and then what we have done, we inserted this in the definition of Lorentz transformation, expanded and ignore all the terms, which is omega square order, and show that this is a antisymmetric matrix. Also, the trace of it vanishes. So let's repeat that same exercise again in terms of this component notation. So let's start with the defining relation of this Lorentz transformation, which in the component form takes the following: sigma remember it is coming from lambda transpose eta times lambda, but you have to be careful about the index positioning while doing this matrix multiplication. And if you apply whatever we discussed in previous lecture, you will get in component. So please go back and try to write this equation by yourself once more time. And now if you insert this here and expand and throw away all the term which is omega square, then you will get omega mu plus omega mu. Please do the algebra. It's very easy to do that. We are leaving that as exercise for you to do. And also, of course, we have used the index raising and lowering using the metric and the inverse metric. And this says that omega is antisymmetric. Because remember that this is like omega mu is equal to minus omega mu. You have interchanged the index, but it is giving you a minus. So this is the antisymmetric metric. And also, let's see what happens to the trace. So what is the trace of the matrix? So omega is a matrix. So trace is the sum of the diagonal element. Diagonal elements means when mu and nu is equal to each other. That means trace of this thing is the following: omega 0, omega 1, omega 2 plus omega 3. This is the nothing but the trace of this omega matrix. Now we have omega mu plus omega mu equal to 0. And let's contract this equation with eta. Suppose, so what that will give, if we contract eta plus mu, it will give eta this. Now we discussed that we can use the inverse matrix to raise the index, and this is the component of inverse Minkowski matrix. So it will raise this mu index and it will convert it to nu. But now nu is the repeated index, so it's summed over. That means this is giving you the trace. And if you use this equation now and contract with eta mu upstairs, that is the inverse metric, then it says that this is 0, which means omega mu 0. Repeated indices summed over, so this is giving the trace of omega is. Now we said that we can show the same thing by starting from the condition on the determinant of this proper Lorentz transformation. So for proper Lorentz transformation, we have determinant of it is 1. Now you can write this determinant using Levis beta and this component of lambda. So let's write it down. So sigma times 0. This is the definition of a determinant. This is just a generalization of what you have done for a Euclidean case. Now we are in a Minkowski spacetime, so we have 4 indices, and 0 component in the metric comes with the negative signature. But then we can use the fact that for proper Lorentz transformation, this is 1, and we can replace this, each of this delta by this expansion. And again, we can throw away all the term, which is omega square order. Please do that algebra, and you will get from here directly omega 0 plus 1 plus 2 3 equal to 0. So trace vanishes. Okay. So you can see that if you use the component notation, you can do this calculation quite faster compared to what we have done previously while discussing this Lorentz group, etc., by doing a brute force matrix multiplication. Before we finish with a question for you. So let's consider the volume element in this Minkowski space-time, which is denoted by d4x. This is the 4 volume element, which is also can be written schematically as t times dt, which is nothing but tx0 and xy, yz, y dz. It's the spatial. So find out how this transform under Lorentz transform. And from this you show that only under proper Lorentz transformation this d4x remains intact. So we leave this as an exercise for you to do. For this you have to use the fact that you can represent this volume element in terms of this Levi-Civita tensor, and we leave it for you to figure that out and complete this exercise. Thank you for listening. We will end.